Hi everyone, I'm going to continue the lecture that was interrupted by the fire alarm today. What we did in class was mostly talk about the GPIO ports again, the general purpose IO ports. We talked about directions, how they're memory mapped to the IO, that ARM is a load store architecture, and then we went through the details of how to initialize port F, and we started to do some assembly on the board, specifically talking about the load store instructions and some of the logical operations that we need. What I would like to do now is finish the lecture by redoing a little bit of the assembly for continuity and then doing a design example of how to use the general purpose IO port by going through a very simple example of what a NOT gate looks like. In class, ARM has a very large number of instructions. It's not an instruction set that's necessarily very easy to learn. So what we're doing in class is constraining ourselves to using a subset of those instructions. We'll limit ourselves to a subset called thumb2 instruction set, which is something that ARM had already defined on their own, which is relatively short and straightforward to understand. ARM did this because the full instruction set takes up more encoding space, so it's less efficient to store the programs and execute them on very simple microcontrollers, which is something that is important for embedded systems, whereas the thumb2 instruction set is smaller and therefore runs better and takes up less space. As I mentioned in class, you should go and Google for the thumb2 instruction set reference, and that will give you the nice card that you can use as a cheat sheet as you go along and try to figure out what's going on. Of course, the book also has a lot of information, as are manuals that are available online. The ARM assembly format should look very familiar to you. It's quite similar to what you're used to from 306 for the LC3. Each line of the assembly code has often a label, which tells us where it is we are in the program so that we can use it to branch to, use it as a subroutine, or perhaps for a loop. And can have an opcode, which is what operation to perform, and this is one of the instructions that is defined in the architecture, followed by a set of operands. Usually the first operand is the destination. This is going to be where the register that is going to contain the value after the operation is complete. For the most part, it's a little bit different from stores, but for the most part, and sometimes there is an operand that is an immediate, which is specified by this pound sign over here, which is then followed by a number. Another important aspect of every line is the comment. Comments are extremely important because they allow us to document what it is we're doing for ourselves, which is important during the debug process, for others to understand what the code is trying to do, and for maintainability so that we can reuse the code and adapt the code as it's needed. Another important part of the assembler routine is pseudo-ops. These are not designed to be executed by the hardware, but rather they're directives for the assembler as it's assembling the program. Many of them are kind of boilerplate. You can copy them from the examples and use them as is for the labs, and they should work just fine. If you want to understand exactly what they do, come ask me, and maybe I'll get a chance to talk about some of them a little bit more in the future, or just go to Google and ask for the ARM assembler directives reference, which will provide an explanation of all of them. You've already seen some. We talked already about EQU, which allows us to define constants, which is very useful. In some later labs and lectures, we'll use variables in global space, so the global variables, which we will allocate space for or initialize certain values using DCB and DCD. And when we have multiple files in our projects, we will need to use the export and import pseudo-ops to get our labels and our names and our constants used across the different files. Many ARM instructions take 3 operands. There is a destination register, RD, an input register, RN, and then often a third operand, which is called the flexible operand, or the flexible second operand, which I started to explain in class. This can either be an immediate, so it can be a constant. This constant is an 8-bit constant, but you can shift those 8 bits and place them anywhere. So any 32-bit number that can be formed by an 8-bit number shifted to the left is valid as a writing as a constant. In addition, you can write other types of constants of the form that look like this, something like xy 0 0 xy 0 0 and so forth, or 0 0 xy 0 0 xy, and assume x and y are each one hexadecimal number, so xy are 8 bits, or xy 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 xy. Right? So all of those are valid constants that you can write into the immediate field for an opt2. Opt2 can also be a register, and it can even be this weird thing over here, which is registers that are shifted. So you can take something like this, right? Add R0, R1, LSL, logical shift left, by 4, which is equivalent to saying R0 is equal to R0 plus R1 times 16. Right? You can also do shifts to the right. You can do rotates and things of that sort. Look at the manual if you're interested in looking at all the details. This will not be something we use frequently, but you might see it. So I just put it here so that you know what it might mean. When we need to access memory, as I mentioned before, we need to use load store instructions because ARM is a load store architecture. We have multiple addressing modes in terms of how to access those locations. The one that you've already seen is a constant. We can take a load instruction and load a constant into a register using it. This is basically a PC offset, right? So the constant is stored in the ROM along with the program and is read from there and placed into a register. We can have a register and an offset from that register. So this takes a two operands kind of for the sources. There's a register that provides the address and then an offset into it. This is convenient, although it's not required, because you can always just form variables in memory using the standard indexed addressing mode, which is what I showed you in class on the board, which can also be used through memory mapped I/O to access our I/O ports. And of course, there are immediates we can use. If you want to load an immediate other than one of those constants, we'll use a move instruction, which I showed you in class as well. It basically looks like move R1 and then maybe an immediate into it, right, or something of this sort. Right, so this is the decimal one because I didn't put a 0x in front of it. These next few slides that I'm going to scroll through quickly give a few details of how these addressing modes work and what exactly they do in memory. We covered this essentially in class already on the board, so I'm just going to scroll through them. This slide summarizes the different load and store instructions that we will use in the ARM. What I've showed you already are LDR and SDR, which simply take a register to provide the index or the address into memory from which it is that you're going to be loading or to which you are storing. As I mentioned in class, this address is byte addressable, so even though you're going to be reading and writing 32-bit values, the addresses are given using bytes. If you want to read something that is not a 32-bit value from memory, you can actually look at this type and you can add one of these suffixes to your instruction. So for example, if I will write LDR SB R1, R0, I will be reading from address R0 given in bytes, read 1 byte from there, sign extended into a 32-bit register and place the value into R1. And similarly, we can do half words, we can do non-sign extended, and we can even do doubles, double words, which are going to use 2 registers. And this is a more complicated instruction that I'm not going to talk about right now. One interesting thing that comes out of this is if we're reading sub registers, right? So if we're all reading a byte and trying to put it into a 32-bit register, if we're reading 2 bytes, there's a question in terms of how we encode the value into memory. So we can take a word, which is going to be, for example, 32 bits, let's say A, B, C, D in hex, and now we need to put it into memory. So the question is, if I'm trying to do something like this, if I'm doing, let's say, an STR of, let's say this is R1, 1, and I'm putting R1 into a location 0 in memory. Let's say this is stored in R0, so let's say R0 is equal to 0. What will memory look like? So if I draw memory now, I have 4 bytes in memory that are going to represent this. They're going to start in 0, and I have 2 options. One is to put the most significant byte in the front, and the other, which can be completely equivalent, is to put the least significant byte in the front, or the most significant byte at the end, okay, at the highest address. Okay, so this one, this decision in terms of how to encode things is called endianness. It's just a property of the architecture, and we need to decide whether we want to have the little end first. Okay, so this will be little endian, or the big end first. This will be big endian. These are not extremely important for what we'll be doing in class. Generally, things will just work, but it's an important term that I want you to remember that it exists. And if you don't pay attention to it as you work between different architectures trying to use the same types of memories or the same files, very odd things could happen. There are also additional formats of the load and store instructions. There is an immediate that you can add, so that will be an offset from the register, which is very useful when we'll be doing arrays and structures and things of that sort, variables. And you can even take this immediate and you can shift it to the left so that you can make larger numbers. This is useful if you want to have more range out of your immediates and you know that you have a certain data type that's larger. So for example, we can turn this immediate into being words instead of being bytes by adding this LSL, logical shift left, in front of it. If you think about it, the ARM instruction set and the LC3 instruction set are actually not that dissimilar. Both are load-store architectures. Both go and have kind of basic operations that they can do. And these next couple of slides are going to show you the correspondence between some LC3 instructions that you're familiar with and ARM instructions. Right? For example, LC3 has load effective address, right, which you can put PC and offset into R0, and ARM has a very similar instruction which I already showed you, which is LDR R0 and then equal label, right? So it's basically LDR with an equal sign is equivalent to load effective address of the LC3. Right? You can see that we have instructions like load with an offset, a register plus offset. ARM has an equivalent, it's just written a little bit different in assembly. And as you go through these type of instructions, you'll see that overall things should make quite a lot of sense to you. There are some things that are not exactly the same though. For example, ARM doesn't have the load indirects that you saw in the LC3. ARM has multiply, ARM has divide. There's not a not in ARM where there was in the LC3. Instead, you can use an exclusive OR with a constant, right? So if we do an exclusive OR, as I showed you in class, with ones, it flips or does a not of each of the bits one by one. So this is things that you want to consider and remember. Okay. Branches also operate a little bit differently in ARM. The condition codes are not negative, 0, and positive, but rather there is a different type of condition codes. I'm not going to go through them right now, but instead you can look at this slide or look at the manual or look at the book to understand how the branches work and what to do. But there are things like is equal to 0, right? You can do a BEQ, you can do not equal to 0, which is B and E, and similarly there are other branches that are useful that you can try out. One operation that is very useful, and you're definitely going to need it to do the labs and generally to do programming in assembly, are shift operations. ARM has logical shifts, arithmetic shifts, and rotates. These work pretty easily, pretty simply. I just wanted to repeat them and remind you what those work. So there is a logical shift right that is equivalent to dividing a number by 2. This is this instruction over here. The problem is it doesn't work in dividing a number by 2 when you're using 2's complement signed numbers, because you end up turning a negative number into a positive number if you shift this 0 into the most significant bit. So there's another instruction called arithmetic shift right, which repeats this last bit in place and maintains the sign of a number to get that to work. Logical shift left allows you to do multiplies. This works for both signed and unsigned numbers. And then there are rotate instructions. There's a rotate right instruction, which is going to take the least significant bit and move it all the way back to the most significant bit, and also put it into the carry. And then there is rotate right extended, which instead of taking the least significant bit and moving it to the most significant bit, it takes the carry and moves it to the most significant bit. So it allows you to gain 1 additional bit if you need it. As mentioned before, everything you need you can find in the reference sheet, in the various manuals, and in the book. So with all those instructions behind us, let's get back to what we were starting to do, which is switch interfacing. We got interrupted because of the flow of class, and then I could not quite mimic a classroom environment at home with doing a board and such. I haven't quite mastered that particular skill yet, so I went through the slides, and I'm sorry for boring you through them. But let's get back to the switch. We were going to do input and output. We've already initialized the switch. I told you how that to occur, and now we want to go and access it. Right, so over here is actually some C code. You can ignore this for now if you don't know C. We'll start talking about it probably on Wednesday or next week. C is very, very easy. For example, you can see that this single statement that we have here in C is going to be translated into several assembly instructions, which are shown here. So if I want to read a value, let's say I want to read a single bit of port A. Right? So if I want to read from port A, and I want to read bit 6, or the pin 6 of port A, what do I do? So the first thing that I do is it's going to be a memory mapped I/O in a load store architecture. So I need to prepare a register that will hold the address of where the port is memory mapped to. This is GPIO port A data register, which I'm going to put into R0. I can then load the value from the port by accessing the appropriate memory location into register R1. And if I want to end up only with bit 6, right, which is equivalent to the data in pin 6, what I will do is I will use an AND operation with a mask that will have a 1 only in the 6th position. All the rest are 0, which will leave me with just the single bit of the value that I want to have at the end. Okay. So now that we know how to initialize the ports and use them, I want to jump out a little bit, go to a higher level, and talk a little bit about how we build and design systems. Right? So in order to do this, there's actually a cycle in terms of where we go and what we do things. And we start by understanding what the problem is. Right? So we try to figure out what our constraints are, what the requirements are, analyze the problem of what it is we're trying to do, and with that we come up with our initial design. Right? So we have constraints on what our design is and a specification of what the design is. That gives us a design. We then need to express it in some way that others can understand. So we will draw diagrams, things like block diagrams, data flow, kind of various flow graphs that will allow us to understand what's going on, maybe write some pseudocode, which will then leave us to development, which is build the necessary hardware and the necessary software to do so, test to make sure everything works. In fact, if you do things right, you test at every space, right? So every transition you test to make sure things work correctly. And when you finally think you're done, it's actually working, you're going to deploy it into the field, at which point new things are going to evolve and you're going to go through the cycle again. In fact, it's very important that you go through this, design your system in such a way that allows you to continuously evolve what it is that you're doing, so that you can reuse components, evolve them over time, and that leads us to have a modular design. We need to have modules that we can work with, and we want to have testing done on those modules as well. And we'll talk a little bit about how this is done in a little bit, and later in class you'll talk quite a bit more about it when you take 312. So let's go through a very, very simple design example. Let's say we've surveyed the market, we decided there is a very big need to design a function which is going to let us require us to do a NOT. Okay, so we're going to do a design example of a very, very simple NOT gate. Okay, so we're going to use our microcontroller to take an input, flip it, and produce an output. Okay, and what we're going to go is through the design process. We're going to draw the data flow, the flow charts, write a little bit of our software, and then you'll do on your own. We'll get you how to do the simulation and prototyping on the board and make sure that everything works. Okay, so let's do our simple design of the NOT gate. So when we do a design, we need to think about what components are going to be in our system. Okay, so that basically tells us some of what the constraints are, perhaps what the requirements are. We put them together and we come up with the components we can have. In our case, we're going to have our microcontroller, which we're going to be using, and we know that it has ports. So perhaps we have a switch connected to port D0, and maybe we have something like an LED connected to port D3. And we would like to have port D3 equal NOT of port D0. So does this complete the specification of our system? Well, not quite. If we think about it, we need to define also whether we're using positive or negative logic, right? So perhaps we're going to have PD0 is switch in positive logic, and our output is also going to be positive logic. Okay, so if we do that, what do we want? We want to have, if we can write our little truth table here, right? So we can say if the switch is open, right, what is port D0, what is port D3, right, and also closed. So in our case, it's going to be 0, 1, 1, and 0. Okay, so now we've specified our system. We know what the components are, we know how they act and what they behave, and it's time to design our solution, or to think about what the solution is going to be. So in fact, what we're going to do is we're going to build some hardware, in which case we already have it, plus an algorithm to run on this hardware. And when we have an algorithm, we need to specify it, which we can do with flowcharts and pseudocode. Okay? So we can define something called a data flow chart, which tells us how the data flows. In this case, it's a very simple data flow. It will go from port D0 into our main program and out to port D3. Okay. We also can think of the actual, the flowcharts that we're more used to thinking, which will help us define the algorithm. So perhaps we're in main, which is where we start, and then we are going to flow through the various blocks that are going to implement our code. So what's the first thing we're going to need to do when we're thinking about the system is initialize port D, D0 as in positive logic, and port D3 is out, positive logic. Okay? So we've written a block that will tell us what to do in terms of our flowchart. What do we do then? We go and we read port 0, read PD0, do the NOT of PD0, and output to PD3 and repeat. Right? So this is going to be our flowchart. Okay? We can also write this in pseudocode, which we will write in terms of steps. Right? So we can write what main is doing. We can write 1, initialize. I won't go into the details again. 2, read from PD0. Flip, right? Very pseudocode. PD0 for write out to PD3. 5, go back 2, 2. Okay? And now we have our algorithm. Okay? So what is the next step after we do this? The next step is to go towards implementation of the code. Right? So implement in assembly. So how do we do this? We need to look at init. That was one of our blocks or one of our pseudocodes. We've already went through this for port F. It's going to be very similar for port D. If you flip through the slide deck, you'll see how we did this for port F, and you can do the same thing for port D, or you can look at the example that you can download from the web page. If you look at lectures, you'll see NotGate port D. You can download it and you can see what the initialization does. Okay. So after init, we had a code block that does read port D0. So how do we do that? We actually looked at this just a couple of slides ago, right? We're going to have to make sure we have a register that is going to include or have in it the location, right? So we're going to have the location, which we've defined this constant before using an EQU pseudo-op of GPIO port D data R, right, the data register. Okay, then we should have a comment that explains this. I don't have room to write it, and I said it in words. Okay. What do we do after that? Well, we load the value from memory into a register. So we can do LDR R1, and we'll read from R0. Okay, but now we have read 32 bits, where we just want a single bit, which is the bit of port D0. So what do? We'll do a mask, right? So if we do an AND operation of R1 and R1 itself, and an immediate, in this case just 1, we will be left with only the value of the least significant bit, which corresponds to port D0. Okay. So now we're done with the read. Okay. What's the next step in our flowchart? It was, flip the value. How do we do this in ARM assembly? Well, we'll just flip whatever is in R1. So we can write a not, which we don't have, so we'll use an exclusive OR. If we do an exclusive OR of R1, and again R1, and again just 1, we'll flip the least significant bit, which now gives us the negation of what we had before. So we have a not of whatever was in PD0. And then the next step, write output. So write to PD3. Okay, how do we write to PD3? Well, we need to store the value into PD3. Right? But if we store R1 into PD3, we end up with non-friendly code. So if we do something like this, just str of R1 into PD3, this is non-friendly because we stepped over, we killed all other ports, pins of PD0, which is not what we wanted to do. Okay, so what should we do? We need to only turn the appropriate bit on. Okay? In fact, if I did this, it will be very wrong because I need to write to PD3, whereas this is in port 0, okay, in position 0. So how do I get the value to positions 3? Well, we can use shift instructions. Right? So we can take and shift to the left. We can do a logical shift left. Let's write it into R1 again, of whatever the value is in R1, and if we shift it to the left by 1, it will be in position 1, by 2 it will be in position 2, by 3 it will be in position 3. We end up with R1 being in the appropriate position. But again, we cannot do this store because it will be a non-friendly store, and we want to write good code, which means we're not modifying things we're not supposed to modify. We had a specification which says which pins we're supposed to modify. So how do we modify just the bits that we want? Well, in order to do that, what we have to do is have the original value that was in the data register. Unfortunately, I've messed this up because I did LDR into R1 and then manipulated R1, so I lost it. So what I could have done is I could have loaded this into R2, and the first thing I did, I could have just done an R2 here, and now R2 contains the original value. So now we want to have R2 have its original value, and then only have whatever is in R1 negate what was there, right? So how do we do that? We need to create the appropriate masks in order to make sure that we can get that to be correct, right? So we want to modify bit 3, but not modify any of the other bits. Okay, so how do we do that? Well, what we can do is we can AND whatever is in R2, just to be safe. I'm going to use a new register here so I don't have to correct myself later, into R3 what is in R2, which is the original value, and I want to put in here a number that will allow us to keep everything be the same thing that it was before, but have only a 0 at position 3. Right, so that will give us a 0 at position 3, into which we can later OR what it is that we want to do. Okay, so how can I write a 32-bit, in this case, number? It's kind of difficult, but it's port A, and port A has only a small number of pins in it, so let's assume that number is smaller than 8 for the moment, and I'll show you a different way of doing it a little bit later on. But what we can do is just write, let's say it's 8 bits, and we want all of them to be 1 except bit position 3. We can just write a 0, because we don't care what happens in the second byte. We'll write a hex number in 2 bytes, and then what it is that we want to write is something that's equivalent to 1011, right? If we were doing this in binary, which means the number 11, right? So I could just write B here. Okay, so oops, there will be position 2. And so if I write E here, and that will clear out the bit in position 3 and allow us to then do an OR of R3 and R3, the sum of R1, and now we end up with a bit that we wanted to have there, and finally we can store it out into the location of the data register, which the memory mapped IO will then turn the LED either on or off depending on what the switch is. What's the final thing we need to do? We need to branch and have a loop. Right? So we should have put a label here. Right? So we'll put a label called loop, and we'll branch to loop, and we are done. And test this code, do everything that we've done, and figure out what it is. As I mentioned before, you can download this and put it on to your simulator and see that everything works correctly. So you can simulate it and you can build it at the end.